طيب السلام عليكم ورحمة الله وبركاته. Uh, this is we are back. This is Dr. El-Moursy back. We are still in lecture number 15, as it is shown in our plan here. In the last lecture, we just presented the NOR gate. What's the definition of NOR, and how can I convert from any gate to the NOR. So today we will start our lecture by an example through which we will demonstrate how can I convert the circuit from a AND or inverter implementation to a multi-level NOR, which is listed here, the multi-level NOR. So going to our slides, or going to our actually board. So the example on the board here, again, this is actually the table that we have built in our last lecture for the conversion between the three basic logic gates and the NOR. So this is actually the NOR conversion table. I recommend for you either to know how can you drive any of those conversions, or simply just memorize the table. Okay, you should know how can you replacing the AND by an OR. You have to know how can you replace the OR by the NOR. You have to know how can you replace the inverter by an OR. So accordingly, you can actually just give me 1 second here. So as we just mentioned, so this is actually the table of conversion, and I recommend for you to either know how to drive it, or you can simply memorize it. You can do the work either through the circuit or through the equation. This example is a multi-level circuit, as you can see here. The multi-level circuit is actually any circuit that is not two-level. That means it is not in any of the standards. It's neither SOP nor POS. And this is exactly the example that we already solved in the lecture, but for the conversion to multi-level NAND. Now we will learn how to convert the exact same circuit from a general multi-level circuit that uses the inverters, the ANDs and the ORs, into a circuit only using one type of logic, which is the NOR gate in our lecture today. Okay, so the technique is very simple. All what you have to do is, if you are memorizing this table, so it is very easy for you to just go and replace any of the logic gates that you have with its equivalent. So we want to replace any OR and with an OR, replacing any AND with an OR, replacing any inverter with an OR. My recommendation is to leave the inverters till the end of the work. Start with the ands and the ors. So actually what I'm doing here is I take the circuit and I redraw it as it is, okay? So this is another copy of the same circuit. And on that other copy, I will start doing the conversion. So let's start by the simple thing, which is the OR. This table is telling me if I have an OR gate and I want to replace it with an OR, I have to add the two inverters at the output side. So actually, this OR, I will replace it with a NOR, meaning one inverter make it an OR and another inverter to compensate for the logic. So there is no change in the logic. I will repeat doing this for all the OR gates. This as well. I have this converted to an OR and adding one extra inverter here in the wire. Third, here also this NOR adding two inverters. One make the circuit NOR and the other to compensate for the logic. Okay, so I started by the first thing, which are the NOR gate, the OR gates. Then we go to the AND gates. The table of conversion tell me if I have an and I want to replace it with a NOR, that means I have to replace it with a NOR and insert two inverters at the input side. That means we will go ahead here and remove the first AND gate and put its equivalent for the NOR. And I have to add what? I have to add two inverters at the input. Next, another AND. Remove the AND and put two inverters at the input. Remove the AND, the last AND here, and put a NOR with two inverters at the input. Okay, so now comes the conversion for the inverters. Okay, before I replace the inverters, I have to check. Maybe on the circuit, I can cancel some of the inverters. So actually, if I have the same wire with two inverters, those inverters cancel each other, because actually, as we mentioned, okay, complement is going back to the original. When I get the first complement to any parameter as the x a bar equals to x. So those two inverters should cancel each other. This is a Boolean algebra property. So that means I will go into, so I can see here, this wire contains two inverters back to back. One comes from the OR conversion, one comes from the AND conversion. So this inverter will remove this inverter, and the circuit goes back to just a wire between the two gates. Okay, right. What about this inverter? This inverter, I can remove it and send it to the input side. Okay, so at the input, instead of having S, I will have S bar. Then check the other wires. This wire, do you have two inverters or only one? You have only one inverter here. So there is no way to replace it. So I have to think about the other wires. So this wire has three inverters, one red, the original one, and one from the AND conversion. Two of them will cancel each other, and the remaining one will stay the same. Okay, so I have to replace it as well. This inverter as well, there is no replacement for that. So now, since I canceled the inverters with each other, okay, I can go and replace the inverters with their NOR implementation. Okay, there are some simple simplification that you can do. You see two inverters for those wires. So I can remove those two inverters and replace the inputs to be input bar. So here I will have C bar, D bar. Okay? And now comes the conversion for the inverters. These 1, 2, 3 inverters has no analogous inverters to cancel them. So I have to remove them and replace them with NOR gates. So this one will be removed and replaced with a NOR and connecting both inputs to the wire. Okay, here this is already cancelled, so it's a wire. Okay, this is one. The other thing is here, this also. I will remove the inverter and replace it with an OR gate with two inputs connected to the same wire. Same thing, we'll do it here. Okay, so due to the space, I will just have the NOR gate here. Okay, two inputs connected together and coming from here, and the output is connected there. Okay, so the circuit now, if you look at the circuit, you will find no other logic gates other than the NORs. So I converted the AND or inverter circuit to an all NOR implemented circuit. Now the question, why we call it multi-level NOR? Because actually the circuit that we have achieved here, originally the circuit was not 2 tau. Originally the circuit is not 2 level. It was actually 4 level or 4 tau delay. The propagation delay from the inputs to the outputs are 4 tau. Now after this conversion, what actually I did for the delay? Did I get the delay worse or better? Okay, so there is no final answer for that. You have to analyze the circuit to see whether the delay is getting higher or lower or maybe stay the same. Okay, this technique of the conversion actually achieve only one goal. This goal is that all the circuit is implemented using NORs, but it may not have an advantage in area or delay. So let's do a quick analysis for the circuit here. Let's take the different branches and study, as we did for this, study the delay and the area. If I take this S branch, I have to go and test each and every branch from the inputs to the output. If I take this branch, I have 1 tau, 2, 3. So the delay for this branch is now turned to be 3 tau. Those two branches is 1, 2, 3, 4. So I have 4 tau here. Those branches are 1, 2, 3, 4. So I have also here 4 tau. Finally, from A and B bar, I have 1, 2, 3, 4, 5. So the delay here is 5 tau. So the total delay of the circuit is getting increased. Okay, the circuit has 4 tau delay. Right now, the circuit is 5 tau delay, because we are looking for the critical path delay, the longest delay in the circuit, which is coming from A and B bar here. Fine. What about the number of gates? How many gates did I achieve after this conversion? Did I get the number of gates smaller or larger? Let's count the gates. 1, 2, 3, 4, 5, 6, 7, 8, 9. I ended up of 9 gates. That means this conversion have actually a disadvantage in area, a disadvantage in delay, which means, however, I actually achieved only one goal, which is the one type of delay. Does this mean the NAND and the NOR gates are bad? Are they hurting the circuit more? The answer is not final yet, okay? In order to learn how can I achieve, so right now, to wrap things up, I can actually optimize the circuit in 3 regards. We learned in chapter 2 how to reduce the delay of the circuit. How can I achieve that? By reducing the circuit delay to the minimum delay ever, which is 2 tau delay. How? By putting the equation or the circuit in one of the 2 standards, either SOP standard, sum of product, or POS standard, product of sum. So I achieved the first goal. In chapter 3, we learned also the simplification and the minimization using the K-map. This simplification actually hit 2 birds with one stone. This will achieve the minimum delay, since the K-map helps me to get the circuit in in an LP or in POS standard, which means minimum delay. And also, since we use the K-map simplification, I get the minimum format for the SOP and the POS. Sorry. In this lecture and the 2 before that, we learned a new optimization, which is the one type of logic, which allows us to use or to build all the circuit for only one type of logic. Either all the circuit to be built using the NOR gates, as we have demonstrated today, or building all the circuit using NAND gates, as we have seen in the lecture. But that's why we call this a multi. So let's just erase this. So what we have achieved here is called what? A multi-level NOR implementation. The interesting question now, can I achieve the 3 optimizations together? And the answer is yes. In order to learn that, we still will use the exact same table of conversion. But now we will use the table of conversion, okay, in order to convert the circuit from one of the standards using either one type of logic, either the NOR implementations or the NAND implementations. How can we do that? We will see that, inshallah, in the next lecture. So in this lecture, we have achieved the multi-level NOR, and in the lecture, we will have achieved the multi-level NAND. Okay? And by the way, the technique that we have used here is using the circuit diagram. I'm on the circuit, removing the gates and replace it with the other, removing the gate and replace it with the other. Okay. Another way to do that is using the Boolean algebra. However, this technique is difficult. I may repeat all of the solution using or achieving multi-level NAND and multi-level NOR using Boolean algebra instead of the drawing. But inshallah, in a separate lecture, I will show this. Okay. So today we learned the multi-level NOR, and inshallah in the next lecture we will learn the two-level NAND and the two-level NOR. Thank you.